And hello again. So I'm going to complete reading the book from where we stopped yesterday. Yesterday not we, anyway, decided to skip this chapter because it recommends that you probably must skip it until you read the concurrency part, which of course I'm going to do. And now we are here in address space. So almost we are done with like 40% or 35%. Let's say 40% of a virtualization part. Okay, now in virtualization of memory. Okay, now the abstraction is the address spaces. The address space also is an abstraction. Okay, so in the early days, building computer systems was easy. Why, you ask? Because users didn't expect much. It is those darned users with their expectations of ease of use, high performance, reliability, etc. that really have led to all these headaches. Next time you meet one of those computer users, thank them for all the problems they have caused. I mean, they caused a lot of problems, but they also created a lot of jobs. You know. So the problems of users are what? What is the opposite of problem? Anyway, if something is a problem for a user, it's a good thing for the programmer. Okay, so early systems. From the perspective of memory, early machines didn't provide much of an abstraction to users. Basically, the physical memory of the machine looked like what you see in figure 13.1, page 2. Okay, let's look at it later. The operating system was a set of routines, library, really. That sat in memory as physical address 0 in this example, and there would be one running program, a process that currently sat in physical memory, starting as physical address 64 kilobytes in this example, and used the rest of memory where there were few illusions here, and the user didn't expect much from the OS. Life was sure easy for the OS developers in those days, wasn't it? Multi-programming and time sharing. After a time, because machines were expensive, people began to share machines more effectively. Thus, the era of multi-programming was born, in which multiple processes were ready to run at a given time, and the operating system would switch between them. For example, when one decided to perform an I/O, doing so increased the effective utilization of the CPU. Okay, such increase in efficiency were particularly important in those days where the machine cost hundreds of thousands or even millions of dollars, and you thought your Mac was expensive. Soon enough, however, people began demanding more of machines, and the era of time sharing was born. Okay. Specifically, many realized the limitations of batch computing, particularly on programmers themselves. who were tired of long and hence inefficient uh, program debug cycles. The notion of interactivity became important as many users might be currently using a machine, each waiting for or hoping for a timely response from their currently executing tasks. One way to implement time sharing would be to run one process for a short while given access to all memory. Then stop it. Save all of its state to some kind of disk, including all of the physical memory. Wait. Uh, allow some other process state run it for a while and thus implement some kind of crude sharing of the machine. Unfortunately, this approach has a big problem. It is way too slow, particularly as memory grows, while saving and restoring register level state, like the PC general purpose registers, is relatively fast because it is saved, I think, on the kernel stack. Saving the entire memory to disk is brutally non-performant. I am too sleepy. Thus, what we'd rather do is leave processes in memory while switching between them, allowing the operating system to implement time sharing efficiently. As shown in figure, okay, page this. See. Okay, free process C, process B, process A. Makes sense. This is what a normal human born in 21st century would expect, or at least would imagine as a first image of this when start saving this PDF. In the diagram, there are three processes A, B, and C, and each of them have a small part of the 500 kilobytes physical memory. Keep it, or anyway. Okay, carved out for them. Assuming a single CPU, the OS chooses to run one of the processes. Say A while others B and C sit in the ready queue waiting to run. As time sharing became popular, you can probably guess that new demands. Wait, what? I just realized I read the entire paragraph and I didn't even retain anything. I didn't understand anything. In the diagram, there are three processes. Okay, carved out for them. Assuming a single CPU, the OS chooses to run one of the processes. Okay, say A, while others B and C sit in the ready queue waiting to run. Okay, as time sharing became more popular, you can probably guess that new demands were placed on the operating system. In particular, allowing multiple programs to reside concurrently in memory while protection and make while in memory makes protection an important issue. You don't want a process to be able to read or worse, write some other process's memory. The address space. the address space. However, we have to keep those pesky users in mind. And doing so requires the operating system to create an ease of use abstraction of physical memory. Okay, so we want to make the memory accessible, easy to use, and secure. We call this abstraction the address space. And it is the running program's view of memory in the system. Understanding this fundamental operating system abstraction of memory is key to understanding how memory is virtualized. Um, anyway, I was talking with someone on WhatsApp. Okay, so however, to we keep to have those pesky users in mind. And doing so requires the operating system. Okay, like this. We call this abstraction the address space, and it is the running program's view of memory in the system. Understanding this fundamental operating system abstraction of memory is key to understanding how memory is virtualized. The address space of a process contains all of the memory state of the running program. For example, the code of the program, the instructions, have to live in memory somewhere, and thus they are in the address space. The program, while it is running, uses a stack to keep track of where it is in the function called chain. Where it is. as well as to allocate local variables and pass parameters and run values as it runs to and from routines. Finally, the heap is used for dynamically allocated user managed memory, such as that you might have received from a command malloc. We can see and new in Objects.OS, C and Java. Of course, there are other things in there too, but for now, let us just assume those three components: code, stack, and heap. In the example figure 13.3, we have a tiny address space, only 16 kilobytes. The program code lives at the top of the address space, starting at 0 in this example, and is packed onto the first 1 kilobyte of the address space. Code is static, thus easy to place in memory. So we can place it at the top of the address space and know that it won't need any more space as the program runs. Right. Program code, heap, free, stack. Is this just the virtual layout? This is just the virtual layout, right? We have a tiny address space. The program code lives at the top of the address space. Wait. Oh, okay. So this is okay. The address space of a process contains only the memory state of the running program. For example, the code program living somewhere. Thus, they are in the address space. The program, while it is running, uses a stack to keep track of where it is in the function call chain, as well as to allocate local variables and pass parameters and return values to and from routines. Finally, the heap is used for dynamically allocated user managed memory, such as that you might receive from a culture malloc or new okay. Of course, there are other things in there to statically initialize the variable, but for now, let us just assume those three components: code, stack, and heap. In the example in the figure 13.3, we have a tiny address space on okay. The program code lives at the top of the address space. Okay. Heap segment contains malloc data dynamically. It grows positively. Okay, so 1 kilobyte, 2 kilobytes, 3, and so on. The stack grows negatively. The stack segment contains local variables, arguments to routines. Return values. Code is static, easy to place memory, so we can place it at the top of the address space and know that it won't need any more space as the program runs. Next, we have two regions of the address space that may grow and shrink while the program runs. While those are the heap at the top and the stack at the bottom, we place them like this because each wishes to be able to grow. And by putting them at the opposite ends of the address space, we can allow such growth. They just have to grow in opposite directions. The heap thus starts after a code at 1 kilobyte and grows downwards. However, displacement of stack and heap is just a convention. You could arrange the address space in a different way if you'd like. As we'll see later, when multiple threads coexist in a address space, no nice way to divide the address space like this works anymore. Of course, when we describe the address space, what we are describing is the abstraction that the operating system is providing to the running program. The program really isn't in memory as physical address 0, though the running rather it is located as some arbitrary physical addresses. Examine processes A, B, C, and there you can see how each process is loaded into memory at a different address, and hence the problem. How can the OS build this abstraction of private, potentially large address space for multiple running processes on sharing memory on top of a single physical memory? Okay, when the OS does this, we say the OS virtualizing memory because the running program thinks it is loaded into memory at a particular address, say 0, and has potentially a very large address space. The reality is quite different. When, for example, a process A in figure K tries to perform a load at address 0, somehow the operating system in tandem with some hardware support will have to make sure the load doesn't actually go to physical address 0, but rather to physical address where A is loaded into memory. This is the key to virtualization of memory, which underlies every common computer system in the world. Okay, goals. What thus we arrive at the job of the operating system. In this set of nodes, to virtualize the memory, the operating system will not only virtualize memory, though it will do so with style. To make sure the operating system does so, we need some goals to guide us. We have seen these goals before. Think of an introduction, and we'll see them again, but they are certainly worth repeating. One major goal of virtual memory system is transparency. The operating system should implement the virtual memory in a way that is invisible to the running program. Thus, the program shouldn't be aware of the fact that memory is virtualized. Rather, the program behaves as if it has its own private physical memory. Behind the scenes, the operating system and the hardware does all the work to multiplex memory among many different jobs, and hence implements the illusion. Another goal of virtual VM is efficiency. The operating system should strive to make the virtualization as efficient as possible, both in terms of time, i.e., not making the program run much more slowly, and space, not using too much memory for structures needed to support virtualization. I think it's because it's not trivial to virtualize memory in this sense. If you make the operating system intercept every call to write something to the memory, it would be hella inefficient. And of course, I know there is TLBs, but I have some basic understanding of them, but not in depth because I was not paying attention enough during the operating system class. Not it's not like my fault. We were studying a lot of garbage with it. Anyway, some other garbage courses, I mean. Both in terms of time, okay, in implementing time efficient virtualization, the operating system will have to rely on hardware support, including hardware features such as GLBs, which we will learn about in due course. Finally, a third virtual memory. Wait. Finally, a third virtual memory goal is protection. The OS should make sure to protect the process from one another as well as the operating system itself from processes. When one process performs a load, store, or instruction fetch, it should not be able to access or affect in any way the memory content of any other process or the OS itself. That is anything outside its address space. Protection thus enables us to deliver the property of isolation among processes. Each process should be running in its own isolated cocoon, safe from the ravages of other faulty or even malicious processes. In the next chapters, we will focus our exploration on the basic mechanisms needed to virtualize memory, including hardware and operating system support. We will also investigate some of the more relevant policies that you will encounter in operating systems, including how to manage free space and which pages to kick out of memory. When you run a low on space, same thing again, I didn't understand anything. I didn't even pay attention. Mhm. Protection thus enables us to deliver the property of isolation among processes. Each process should be running in its own isolated cocoon, safe from the ravages of other faulty or even malicious processes. In the next chapters, we will focus our exploration on the basic mechanisms needed to virtualize memory, including hardware and operating systems support. We'll also investigate some of the more relevant policies that you will encounter in operating systems, including how to manage free space and which pages to kick out of memory. When you run low on space, in doing so, will build up your understanding on how a modern virtual memory system really works. Summary. I feel like just the introduction almost wait Just the introduction fried my brain. Um, Virtual memory, the VM system, okay. Well, we have seen in the introduction of major operating system subsystem, virtual memory. The virtual memory is responsible for providing the illusion of a large, sparse private address space to each running program. Each virtual address space contains all of the program's instructions and data, which can be referenced by the program via virtual addresses. The OS, with some serious hardware help, will take each of these virtual memory references and turn them into physical addresses, which can be presented to the physical memory in order to fetch or update the desired information. The OS will provide this service for many processes at once, making sure to protect the programs from one another. To enable this approach, to enable to entire what the entire approach requires a great deal of mechanisms, lots of low-level machinery, and some of critical parts. Okay, let's start from the bottom up, describing the critical mechanisms first, and thus we proceed. Wait, where is it? Okay, so if you make it through virtual memory, you will likely make it all the way. I hope so. I think there is something. There is another one. I didn't read. Where was it? Okay, so wait. This one, I read it. I think it is this one. Isolation is a key principle in building reliable systems. If two entities are properly isolated from one another, this implies that one can fail without affecting the other. Operating systems strive to isolate processes from each other and in this way prevent one from harming the other. By using memory isolation, the operating system further ensures that running programs cannot affect the operation of the underlying operating system. Some modern operating systems take isolation even further by walling off pieces of the OS from other pieces, such as microkernels. Thus, we may provide greater reliability than typical monolithic kernel design. Okay, let me see this. Aside, every address you see is virtual. Ever write a C program that prints out a pointer? The value you see, some large number, is often printed in hexadecimal, is a virtual address. Ever wonder where the code of your program is found? You can print that out too, and yes, you can print it. It is also a virtual address. In a virtual address, it's only the operating system through its tricky techniques of virtualization memory that knows where the physical memory of the machine. Okay, so never forget, if you print out an address in a program, it's a virtual one. It's an illusion of how things are laid out in memory. The operating system and the hardware knows the real truth. Here is a little program that prints out at the location of the main routine where code lives. The value of heap allocated value returns from malloc, and the location of an integer on the stack. When you run on a 64-bit machine, you use from this you can see the code comes first in the address space, then the heap, then the stack. Code, heap, and stack. As are virtual, they will be translated by the operating system and hardware in order to fetch values from their true physical locations. References. In this homework, we'll just learn few useful tools to examine virtual memory on Linux-based systems. This will only be a brief hint at what is possible. You will have to dive deeper on your own to truly become an expert, as always. The first Linux tool is free. Okay, I know this. Free? What? It's short, don't worry. Now run free, perhaps using some of the arguments. Which? Is this a command? No. What? Wait, let me see. Display memory total in megabytes. How much memory is in your system? How much is free? How do these numbers match your intuition? Okay. Total used free. I can just do a new fetch and get this information. Anyway, let's create a little program that uses a certain amount of memory called memory user. Okay, I guess memory API. I hope this is just about malloc and free. Okay, 12 pages, so it's not going to be a work in the park like the previous one. How long have we been streaming? 40 minutes. What interface are commonly used? Okay, let's continue this memory API. I'll just turn on the AC. In this interlude, we discuss the memory allocation interfaces in Unix systems. The interfaces provided are quite simple, and hence this chapter is short and to the point. The main problem we address is understanding how to allocate and manage memory is critical in building robust and reliable software. Okay. In Unix, okay. What interfaces are commonly used? What mistakes should be avoided? Types of memory. In running C programs, there are two types of memory that are allocated. The first is called stack memory, and allocations and deallocations of it are managed implicitly by the compiler for you. The programmer, for this reason, is sometimes called automatic memory. Declaring memory on the stack in C is easy. For example, let's say you need some space in a function f for an integer called x. Declares an integer on the stack. The compiler does the rest, making sure to make space on the stack when you call into func. When you return from the function, the compiler deallocates the memory for you. Thus, if you want some information to live beyond the call invocation, you had better not leave that information on the stack. Indeed, we hope all chapters are, but is one pointer, we think. It is this need for long-lived memory that gets us to the second type of memory, called heap memory, where all allocations and deallocations are explicitly handled by you, the programmer. A heavy responsibility, no doubt, and certainly the cause of many bugs. But if you are careful and pay attention, you will use such interfaces correctly without too much trouble. Here is an example of how one might allocate an integer on the heap. A couple of notes about this small code snippet. First, you might notice that both stack and heap allocation occur on this line. Yes. First, the compiler knows to make a room for a pointer to an integer where it sees your declaration of a set pointer. Subsequently, when the program calls malloc, it requests a space for an integer on the heap. The routine calls the address of such an integer upon success, or null on failure. Wait, I have a question. I have always thought that malloc is what I think I am. Wait. I always thought that malloc is a syscall. You ask the kernel for some additional space. But now it looks like it's not. Somehow. Because the virtual address space is known and the kernel knows it and knows you might have all of that. The compiler will just like on malloc, it will just go to the heap address space, the free space, and allocate there some allocate there some somewhat some space for your integer or anything. Then the kernel will try to write this. It will hit a page fault because that page does not exist. Then it will allocate one for you. I think this is it. I think, not sure. Let me ask ChatGPT. New chat. Okay. Is malloc syscall or no? I used to think so, but now it looks like it just jumps to heap free location in dual address space, allocate something there. And because touching that memory will trigger a page fault, the OS will intercept it and it will give your program a fresh real memory page to map it for. For what? For your thing. Is that correct? Okay, malloc is not a syscall. Nice. I have always thought that it is a syscall. Anyway, it is a user space allocator function, usually provided by libc. Your mod is mostly correct with a few refinements. When you call this, okay, I'm glad I got a right answer before uh, reading about it. Like, not right answer, right observation. Just from learning about the address space. When you call this, the allocator typically searches its existing free blocks, chooses a suitable block, updates allocator metadata, returns a virtual address. The allocator typically returns search free blocks. When allocator needs more virtual space, it may ask the kernel using syscall such as okay. Wait, so when the allocator needs more virtual address space, it may ask the kernel using syscalls like mmap or I don't know this brick or sbrick. Find reusable free blocks, need more address space. Lazy physical allocation of cell. Okay, the kernel may reserve virtual address space without immediately assigning physical RAM to every page. When your program first accesses the page, the CPU might trigger a page fault because the virtual page does not yet have a physical page mapped. The kernel handles the fault by verifying that the address belongs to a valid mapping, obtaining a physical page, or otherwise backing the page. 01 is for security, adding the mapping to the process page table, resuming the instruction. So this part of your understanding is right. Malloc returns virtual memory. First access causes page fault. Kernel installs physical backing. However, there are important qualifications. Not every malloc causes a syscall. Hmm. What about the very first malloc you write? Like the let's say allocator state checks whether allocator is unstable use the memory. If not, count this return physical address. There is an important detail before main starts. The dynamic loader and libc may already have performed allocations or established mappings, so the first malloc appearing in your source code may not be the process's first allocation. Okay. call. Can it requests nil on failure, which is then stored on the stack for the use by the program. Because of its explicit nature, and because of its more varied usage, heap memory presents more challenges to both users and systems. Thus, it is the focus of the remainder of our discussion. The malloc call is quite simple. You pass a size asking for some room for the heap, and it either succeeds and gives you back a pointer to the newly allocated space or fails and returns none. The manual page shows what you need to do. Use small malloc, type man malloc. Mhm. From this information, you can see that all you need to do is include the header file std to use malloc. In fact, you don't really need to even do this, as the C library, which which all C programs link with by default, has the code for malloc inside it. Adding the header just lets the compiler check whether you are calling malloc correctly. Passing the right number of arguments to it, the right type. The single parameter malloc takes is of type size G, which simply describes how many bytes you need. However, most programmers do not type a number directly, such as 10. Indeed, it would be considered poor form to do so. Instead, the various routines and macros are utilized. For example, allocate space for double precision floating point. You simply do this. That's a lot of doubling. Double, double, double. This is also. Uh, this is generally thought of as a compile time operator, meaning that the actual size is known at compile time, and thus a number, in this case 8 for a double, is substituted as the argument to malloc. For this reason, size of is correctly thought of as an operator and not a function call. Okay, use the size of operator to request the right amount of space. In C, this is generally thought as a compile time operator, meaning that the actual size is known in compile time and thus the number. For this reason, size of is correctly thought of as an operator and not a function call. A function call would take place at runtime. You can also pass in the name of a variable you, and not just type. Choose size of, but in some cases you might not get the desired results. So be careful. For example, let's check. Okay, this is a classic foot gun. uh, yes. In the first line, we have declared space of an array of 10 integers, which is fine and dandy. However, when we use size of in the next line, a change value such as 4 or 8, the reason in this case is size of things we are simply asking how big a pointer to an integer is, not how much memory we have dynamically allocated. However, sometimes size of does work as you might expect. Another place to be careful is with strings. When declaring space for a string, use the following idiom: malloc strlen s plus 1, which gets the length of the string using the function strlen, and adds 1 to it, in order to make room for the end of string character. The size of may lead to trouble here. You must also notice that malloc returns a pointer to type void. Pointers after type void. Doing so is just a way to pass back an address and let the programmer decide what to do with it. The programmer further helps out by using what is called a cast. In our example above, the programmer casts the return type of malloc to a return to a pointer to a double. Casting doesn't really accomplish anything, it just tells the compiler and other programmers who might be reading your code, yeah, I know what I am doing. By casting the result of malloc, just giving some reassurance the cast is not needed for correctness. Free call. As it turns out, allocating memory is the easy part of the question. Knowing when, how, and even if to free memory is the hard part. To free memory, to free heap memory that is no longer in use, program is simply called free. The routine takes one argument, the pointer returned by malloc. Thus, you might notice the size of the allocated region is not passed in by the user and must be tracked by memory allocation library itself. Uh, isn't this everything about it? What are the rest of the pages about? Common errors. There are a number of common errors that arise in the use of malloc and free. Here are some we have seen over and over again in teaching the undergraduate operating system course. All of these examples compile and run with nary a peep from the compiler. What? Anyway, while compiling a C program is necessary to build a correct program, it is far from sufficient, as you will learn. Correct memory management has been such a problem, in fact, that many languages have support for automatic memory management. In such languages, while you call something akin to malloc to allocate memory, usually new or something similar, never have to come something into free space. Or rather, a garbage collector runs and figures out what memory you no longer have reference and freezes for you. Forgetting to allocate memory. Many routines expect memory to be allocated before you call them. For example, the routine destination copies the string from a source pointer. However, if you are not careful, you might do this. Um, if you aren't sure how some routine or operator you are using behaves, there is no substitute for simply trying it out and making sure it behaves as you expect. While reading the manual pages or other documentation is useful, how it works in practice is what matters. Write some code and test it. That is no doubt the best way to make sure your code behaves as you desire. Indeed, that is what we did to double check things size of actually too. What? Where did I stop? Okay, common errors. There are a number of common errors that arise in the use of malloc and free. Here are some we've seen over and over again in teaching the undergraduate operating systems course. All of these are all of these examples compile and run with okay, having such a okay, this one, yes, here it's compiled or it's run doesn't mean it is correct. Just because a program compiled or even run once or many times correctly does not mean the program is correct. Many events may have conspired to get you to a point where you believe it works, but then something changes and it stops. A common student reaction is to say or yell, but it worked before, and then blame the compiler, operating system, hardware, or even, dare we say, the professor. But the problem is usually right where you think it would be in your code. Get to work and debug it before you blame those others, those other components. When you run this code, it will likely lead to a segmentation fault. It is not likely, it is definitely. Not really definitely. Let me see. Yeah, definitely. Which is a fancy term for you did something wrong with memory, you foolish programmer, and I'm angry. Mhm. In this case, the program proper code might instead look like this. Okay. Hmm. Alternatively, you could use a stirred to make your life even easier. Read a stirred in one page for more information. Not allocating enough memory. A related error is not allocating enough memory, sometimes called a buffer overflow. Okay, too small. Oddly enough, depending on how malloc is implemented and many other details, this program will often run seemingly correct. In some cases, when the string copy executes, it writes one byte too far past the end of the allocated space. But when some cases are harmless, perhaps operating a variable that isn't used anymore, some cases these overflows can be incredibly harmful, and in fact, um, the source of many security vulnerabilities in systems. In other cases, the malloc library allocated a little extra space anyhow, and thus your program actually doesn't scale on some other variables value and works quite fine. In even other cases, the program will indeed fault and crash, and thus we learn another valuable lesson. Even though it ran correctly once, doesn't mean it's correct. Forget to initialize or allocated memory. With this error, you might call malloc properly, but forget to fill in some values into your newly allocated data type. Don't do this. If you do forget, your program will eventually encounter an initialized read. Where it reads from the heap some data of unknown value. Who knows um, what who knows what might be in there? If you are lucky, some value such that the program still works. If you are not lucky, something random and harmful. Forget into free memory leak, long run application or systems. This is a huge problem as slowly leaking memory eventually leads to run out of memory. And at which point a system restart is required. Thus, in general, when you are done with a chunk of memory, you should make sure to free it. Note that using a garbage collected language doesn't help here. If you still have a reference to some chunk of memory, no garbage collector will ever free it. And thus memory leaks remain a problem even in more modern languages. In some cases, it may seem like not calling free is reasonable. For example, your program is short-lived and will exit soon. In this case, when the process dies, the eyes will clean up. While this certainly works, it's probably a bad habit to develop. So be wary of choosing such a strategy. In the long run, one of your goals is the program is to develop a good habit. One of those habits is understanding how you are managing memory, and in language like C, freeing the blocks you have allocated, even if you can get away with not doing so. It is very good to get in the habit of freeing each and every byte you explicitly allocate. Freeing memory before you are done with it. Dangling pointer. As you can guess, it is a bad thing. The subsequent, okay, this is easy. free memory repeatedly, double free. As you can imagine, your application might get confused and do all sorts of weird things. Crashes are a common outcome, calling free incorrectly. One last problem we discuss is the call of free incorrectly. A call free expects you only to pass to it one of its pointer is received from malloc earlier. When you pass in some other value, bad things can and do happen. Thus, such invalid frames are dangerous and, of course, should also be avoided. Let me read this. When you write short-level programs, you might allocate some space using malloc, and the program runs and what runs and is about to complete. There need to call free bunch of time you just were exiting. Well, it seems wrong not to do, not to. Memory will be lost in real senses. The reason is simple. There are really two levels of memory management in the system. The first level of memory management is performed by the operating system, which hands out memory to processes when they run and take it back when processes exit. The second level of management is within each process. For example, within the okay, even if you fail to call free and thus leak memory in the heap, the operating system will reclaim all memory of the process, including the okay stack okay when program is finished running. No matter what state of your heap in your address space, the operating system back all of those pages when the process dies, thus ensuring that no memory is lost despite the fact that you didn't fail it. Thus, for short-lived programs, leaking memory does not cause any operational problems. Though it may be considered poor form. When you write a long-running server, such as a web server or a database management system, which never exist, leak memory is much bigger issue and will eventually leak and crash. The application runs out of memory. And of course, leaking memory is an even larger issue inside one particular program, the operating system itself, showing us once again those who write the kernel code have the toughest job of all. Okay. Summary. As you can see, there are lots of ways to abuse memory because of frequent errors with memory. Our ecosphere of tools have developed to help find such problems in your code and checks out both purify and valgrind, both excellent technical sources of memory related problems. Once you become accustomed to using these powerful tools, you will wonder how you survive without them. Underlying operating system concept support. Wait, what is this? You might have noticed that we haven't been talking about system calls when discussing malloc and free. The reason for this is simple. They are not system calls, but rather library calls. Thus, the malloc library manages space within your virtual address space, but itself is built on top of some system calls which call into the operating system to ask for more memory or release some back to the system. One such system call is called break, which is used to change the location of the program's break. The location of the end of the heap. Okay, this is interesting. It takes one argument. Um, it takes one argument and address of the new break, and thus either increase or decrease the size of the heap based on whether the new break is larger or smaller than the previous. An additional call sbrek is passed an increment but otherwise serves a similar purpose. Note that you should never directly call either break or sbrek. They are used by the memory allocation library. If you try to use them, if you try to use them, you will likely make something go horribly wrong. Stick to malloc and free instead. Finally, you can also obtain memory from the operating system via mmap call. By passing in the correct arguments, mmap can create anonymous memory regions within the same program. A region which is not associated with any particular file but rather with swap space. Something we'll discuss in detail later on virtual memory. This memory can then be treated like a heap and managed as such. Read the manual page of mmap for more details. Other calls. There are a few other calls that the memory allocation libraries support. For example, clloc can allocate memory and zeros it before returning. This prevents some errors where you assume that memory is zeroed and forget to initialize it yourself. See the paragraph. Okay. Routine realloc can also be useful when you've allocated space for something, say an array, and you need something to add something new. Realloc makes a new larger region of memory, copies the old region into it, and returns the pointer to the new region. Summary. We have introduced some of the APIs dealing with memory allocation. As we just covered the basics. More details are available elsewhere with cbook. Okay. I just came from with memory allocation. Okay, I have this thing for grind. Yeah, just sanitizers in Clang or GCC are enough, I think. Okay, finish this one. Memory API, address translation, segmentation. Okay, the next chapter is the beginning of the end. An hour and a half. I think I have no idea if we should take some break or just end up the stream. I feel tired. I was not even planning to stream, just one person encouraged me to do so. Okay, this is 15 pages, so it's going to be a hassle to understand. Okay, this is summary. That was a very long summary. I think this is it for today. Hmm. Let me see this virtual machines. Virtual machine Windows. Okay, I think this is it for today. Um,